within the other dimension, parallel to the surface, these profiles will be quite smooth. So a pulse profile is a series of smooth disks, if you like, of different size, travelling throughout the medium. So if this is a circular transducer, then these will be circular as well. So you've got to consider that there's a series of circular regions travelling through the tissue. They might be increasing and decreasing in size as they travel. Due to this focusing here, these little discs become shorter, then they become broader again. That's what the sort of mental image you need to carry in your head, what a pulse profile looks like. That you should see quite sophisticated. Now, from a safety point of view, if we want to be able to calculate what is the intensity at this point, what's the maximum intensity that I might be subjecting my patient to, then you need to take into account that there is this quite complicated profile. Now, to do this, we define a point within the pulse at which the intensity is greatest. And this is probably going to be at some point in the middle of the pulse. This has the greatest intensity in this direction, and this has the greatest intensity in that direction. So it's going to be some point right in the centre about there. And that is known as the spatial peak. So we define that pulse as having a point within it at which the intensity is the highest. And we also consider the fact that the pulse is moving in this direction, and where it is focused is where the pulse is smallest, and that's where we expect the intensity to be greatest. So there is no other position along the axis where the intensity is greater than it is here. So it's going to occur at the focus, probably right in the middle. So we call this point within the tissue the spatial peak. And thus, going back here, the spatial peak temporal average and spatial peak pulse average refer to that specific location, that unique location within the tissue, which we call the spatial peak. Yeah?
Says in the notes that broadly doesn't necessarily locate the beam axis to the focus.
Well, that's where it's perfectly ideal system, particularly if you're talking about phased arrays. The actual pulse profile is a lot more complicated. They're not perfectly circular. It's going to be a challenge. And also, it also depends on the tissue you're covering. Okay, so the spatial peak temporal average is equal to the time average intensity at that location. So you measure your intensity over all time, and then you divide by that time. So you've got a whole series of pulses travelling through that point. Then you say you do your measurement for 10 minutes, and you divide by 10 minutes, and that is your average intensity over all time. Okay. The spatial peak pulse average, you just average over the pulse length. So it is just the average intensity over the length at which the pulse travels through that point. So you discount any of the time where the pulse isn't there. So the pulse arrives at that spatial peak, travels through that position, and then leaves. And you just do your average over that time at which that point is exposed to the pulse. So you expect it to be a much greater value, because we're only averaging over when the pulse is there. You're not including all the time for which there is no pulse at that location. And third definition does not refer to the spatial peak position. Instead, is averaged over all time and over the entire beam cross-section. So you take a given cross-section and you average the intensity over that cross-section area. And that depends on obviously the point in the beam which you calculated. And that will change along the beam axis. Okay. So you need to define those. Then it says which of these parameters would you use to to estimate the rate at which a given organ is heated during an ultrasound scan, where you would use the last of those, the spatial average temperature, to essentially that would give you the watts, the energy per unit time, the quantity of tissue. Then there's a question, calculation. Consider a 3 megahertz ultrasound transducer emitting pulses with a spatial peak pulse average intensity of 50 milliwatts per square centimetre at a rate of 8 kilohertz. If the quality factor of the transducer is 12, calculate the spatial peak temporal average intensity. Calculation very similar to one of the notes. Well, pulse length, reminder of pulse length is equal to quality factor times wavelength. So the quality factor of a pulse essentially is the number of wavelengths contained in a pulse. It's typically a number of the order of 10, 5 or 10 for medical imaging system. So Q lambda is the pulse length, lambda is velocity divided by frequency, and the pulse duration, the time at which it takes for a pulse to pass a given point, is going to be the pulse length divided by velocity. Therefore, combining those two, the pulse length is going to be equal to the quality factor divided by the frequency, and thus equals 4 microseconds. In other words, it takes 4 microseconds for that pulse to pass a given point in the tissue. Now, this formula is given in the notes. If you don't remember it in the exam, it's possible that you could derive those principles. Spatial peak temporal average intensity is equal to spatial peak pulse average intensity times pulse duration times the pulse repetition frequency. That's the rate at which pulses are emitted into the tissue, and we're told that's 8 kilohertz. And therefore, put those numbers in, and you get the spatial peak temporal average comes out as 0.48 milliwatts per square centimetre. Relatively straightforward calculation. Okay, finally, final ultrasound question on this paper. Briefly explain the operating principles of the treatment method known as high-intensity focused ultrasound, describing the physical mechanisms involved. Wasn't expecting very much. I think it wasn't worth very many marks, it's very straightforward. I'd hope to get a diagram something like that, where you show a relatively large transducer focusing very heavily down to as small a point as possible and as quickly as possible. And so as the ultrasound waves are focused, the intensity obviously increases, and you can get a lot of energy deposited in a very small volume, and therefore produce quite strong pressures and temperatures at that point. It asks you to describe the mechanisms involved, as I described in the notes, that in principle you can achieve intensities high enough to generate cavitation. In most high-flow applications, they try to avoid cavitation because cavitation is rather unpredictable. It can produce damage which is difficult to predict. Therefore, it's generally, the damage is principally thermal. So you generate such high temperatures at the focal point that the tissue is destroyed through thermal heating. More formally by a process known as coagulation process. Process just means tissue damage. Okay. I name a common clinical application of HIFU, that one that is being led at the moment at UCL. It's one of the centres that's trying this with some success, and that's in treatment of prostate cancer. Final calculation at the end. A HIFU transducer operating at 4 megahertz is a diameter of 10 millimeters and uses an acoustic lens with a range average temporal average intensity of ultrasound entering the tissue at the surface of the transducer is 1 watt per square centimetre. Estimate that intensity at the focus. You just need to determine the size of the focal spot. And there is a formula for that in your notes. The width of the beam at the focus is approximately equal to r lambda over A, where r is the radius of curvature of the lens, and A is the radius of the transducer. Now you're given all those things in the question, and you can calculate lambda, velocity divided by the frequency. And thus the width of the beam at the focus comes out as 0.77 millimeters, and the area has decreased by a ratio of the square of the widths. So the diameter of the lens itself is 10 millimeters. That is now reduced to a size of 0.77 millimeters. Well, the ratio of the areas is going to be a ratio of their squares. So 10 over 0.77 squared, which is about 169. So the area of the beam has been decreased due to focusing to a factor of about 169, and therefore the intensity has increased by an amount, by a ratio of 169. So you can see you can get a very considerable amount of energy deposited in a very small area. It's about 169 watts per square centimetre. It's a lot of energy being deposited in the cell. That's it. Okay. Well, I know Karen's going to be along in about 5 minutes to go through the MRI material. If you have any questions, I am available certainly Monday and Tuesday next week. If you'd like to email me and arrange time to come and see me, I'm very happy to